Okay, the next big question that you'll be tested on will be what's called the scalar product or the dot product. Now, don't worry, you are given these at the front of your sheet, so you don't really have to remember them. All the scalar product or the dot product means is that you're multiplying together your two vectors. Okay? I mean, you can't really do that exactly because you can't just multiply vectors together because they've got magnitude and direction, but that's why we call it the scalar product. And we usually use this to work out the angle in maths because the scalar product is also equal to the magnitude of the vectors multiplied by the angle between them. And what's not given to you in your paper is just a little drawing to maybe explain what's going on. And if we've got an angle in here, theta's in there, and say I called this vector A and vector B, that's fine. Or also the two vectors could be pointing. Right, sorry, I do kind of do that a lot actually. Sorry. There we go. Put it at the end rather than the middle. The two vectors can be pointing towards the point as well. That is permissible. So again, that could be the angle, that could be A, that could be B. That is also fine. What is not fine is to have the angles pointing in different directions. So if you're actually in a situation where you've got something like this, where you've got a vector coming in and a vector going out, what you'd have to do then is rearrange to make sure that the vectors go together. So what you can do is take this vector here and actually then move it back the way like this. Okay, so that would then be okay to work out this angle in here by just moving this vector down. And then you could use your 180, take away this angle to work out that angle. What you couldn't do is use this to work out this angle because they're not pointing to the same point. Okay, so you'd have to move this vector here, is called vector A. You'd have to move that back the way so that now it's pointing towards this point. Okay, so see, they're all pointing the same way. We'll call that vector B. Okay, so that's what you're going to be tested on. That looks very complicated, doesn't it? Really, but really, it just means that you're timesing them, adding them, timesing them, adding them, timesing them, adding them. Nice and simple. I mean, remember the magnitude is like Pythagoras; it's the square and the square root as well. Okay. So let's have a little look to start. I'll find an expression for u dot b. So they're trying to lead us into the question, which is very nice. So I would say, okay, right, u dot v, the scalar product means that I'm multiplying together these and adding them, multiply and add, multiply and add. So that'll be the same as p multiplied by 2p plus 16 multiplied by, I'll just say negative 2 times negative 3 is 6, and 4 times 6 is 24. So my expression then, I'm going to have 2p squared plus 16p, because I'm multiplying together this and this. And this is where your little algebra from Nat 5 comes in quite well. You need to make sure you know these rules back of your hand. And that is plus 30. So that's a nice little expression for u and v. And now it's in terms of values for which this is perpendicular. Well, for perpendicular vectors, theta is going to be 90. Okay, so if I've got perpendicular vectors going like this, doesn't matter if they're going in or out, that's 90. If I was to do cos of 90, let's remember my cos graph, again, that 5, we should know that that goes up to 360, which means the middle is 180, which puts this bit here as 90. So if I was to do cos of 90, I would get 0. In the same way, if I did cos of 270, I would also get 0. In the same way, if I did cos of 180, I would get negative 1. If I did cos of 0, I'd get 1. Cos of 360, I'd get 1. So cos of 90 gives you 0. So the scalar product for perpendicular vectors is always going to be 0. Okay, so I would be starting off by saying, for part B, I'd be saying that 2p squared plus 16p plus 30 is equal to 0 for perpendicular vectors. I've just done a little perpendicular symbol there. You could write it, I'm being lazy. Yeah. And now we've got a quadratic equal to 0. We're going to have to factorise. So best way to do that is to take out your common factor of 2. Always take out a common factor first if you can. that's equal to 0. And then you're looking to add to 8 and multiply to 15. What two numbers do that? Well, that will be, what's that? 5 and 3. So p plus 5 and p plus 3. So it's asking the values for which it could be perpendicular. Well, to solve this then, I'm saying that, well, p plus 5 is going to have to be equal to 0, so p would be equal to negative 5, and p would be equal to negative 3. All I'm saying here is each of these brackets would be equal to 0 for this to become 0, because 0 times this would be 0. So, you know, if you want to go longhand, p plus 5 equals 0, rearrange it. But basically, you know, be cheat as you're changing the signs. And that's your two answers for that. Last question then. Determine the value of p for which u and v are parallel. The value, we'll run out of space, I'll just get some more space. Okay, I made a bit more space there. So, parallel, very similar to the collinear question that we had before. Actually, you know what, maybe I'll just do it here. Yeah, because otherwise it would be too far away from the question. So very similar to the collinear question. So if we were to take a common factor out, so I could actually take out a 2 from that vector. And that's going to give me p over 2, negative 1, and 2. So you're trying to take out the biggest number that you possibly can to get to the root of the vector. Okay, so if you think about this vector here, that is, I'll draw it in a wee sec actually. So I'll draw it in a wee sec. We'll do the same on the other one. I'm going to take out 3. So I'll say I'm going to take out 3, and that's going to be 2p plus 16 divided by 3, and negative 1 and 2. So you see there's like, we've now got the same base vector. So what I've drawn there is vector u and vector v. Now, you can think on that. Okay, so I've got 2 of this kind of this base vector over here. That's going to be my u. Okay, so u is made up of 2 of these, v is made up of 3. So I'll draw that in green. So I've got 3 of those base vectors. That's your v. Yeah, that's what that means. You've got 3 of this kind of unitary value, not unitary, this kind of makeup value, this base value. Okay, and I've got 2 over there. So if you've got that common vector, you know that they're parallel. So I'm just going to rub that out just now. So at that point, I'd be saying, well, p over 2 is going to equal 2p plus 16 over 3 for parallel vector. Yeah. And then we're back to nat 5. Yeah, I'm timesing by 3 and I'm timesing by 2. I'm kind of, it's effectively cross multiplying, you know, I'm moving the 2 up here and I'm moving the 3 up to the other side. So I'm going to end up with 3p, which is equal to, and if times outside by 2, it's 4p plus 32. Yeah? And take my p's to one side, so I get negative p is equal to 32. Oh, sorry, we'll leave it like that, that's not very good. Times everything by negative 1, so p is equal to negative 32. And let's check our answers are okay. There we go, fantastic. So, quite a nice question that, there's a wee bit in it. The first thing you want to know is that when you see the scalar dot product, you have the equations in front of you. You have the big equation. Remember, this is magnitude, which is you square the terms and add them together, root them. It tells you what the dot product is here. Effectively multiply them and add them. So whenever you see this, you should be thinking, get my equation written down. Don't panic. They like to throw in a lot of quadratics at you at higher. So things like this will come up. And the way you solve quadratics is by factorizing. You always take a common factor, and then you decide, is it a difference of 2 squares? Is it a trinomial? Every single time. Okay, difference of 2 squares, trinomial. But take your common factor first. And the last one, whenever you're talking about parallel vectors or collinear vectors, you want to find this base, this root vector, yeah? And from there, if those base root vectors are the same, you know that it's parallel. And from that, you can solve it, because you know this should be equal to this. Okay, I think we'll do one more of them in the next video.